So far we've seen a couple of different methods for finding antiderivatives. Those have included W substitution, which is based on the chain rule, and integration by parts, which is based on the product rule. Today we're going to take a look at the method of partial fractions, and this is based on the idea of finding common denominators when adding fractions. So the method of partial fractions is designed to be used with rational functions. The method takes advantage of the idea of adding fractions by finding a common denominator. And the idea behind the method is to figure out a way to undo finding a common denominator to get back to what we think of as the original fractions. What will end up happening is we'll take the integral of a difficult function, a rational function, and we'll replace it with integrals that are much easier to do. The next slide will provide some of the common integrals that we'll end up with after doing partial fractions. And these are integrals that hopefully we'll be able to recognize and do without too much trouble. So when we integrate by partial fractions, we end up with a fairly short list of common types of integrals. So for example, the integral of 1 over x we'll need to remember is the natural log of the absolute value of x. And similarly, something like the integral of 1 over x plus 2, that would be the natural log of the absolute value of x plus 2. An integral like 1 over x minus 1 squared, we have to be careful here that we don't automatically start writing down a logarithm because this is actually an example where we would need the power rule. So we could rewrite x minus 1 squared that's in the denominator as x minus 1 to the negative 2 in the numerator, apply the power rule, and we would get minus 1 times x minus 1 to the negative 1 plus a constant. Often we would rewrite that as negative 1 over x minus 1 plus a constant. For any other power, things would work the same way. So integral of 1 over x plus 4 cubed, that would end up being minus a half x plus 4 to the negative 2, or negative 1 over 2 times x plus 4 squared plus c. So these are just specific examples of the kinds of integrals we'll see. Basically, they're going to fall into one of two types, either those involving a power of 1 in the denominator, in which case we have a natural log for the antiderivative, or those that involve a power other than 1 in the denominator, in which case the power rule will apply. So we want to talk a little bit about polynomials and rational functions to review some terminology and notation. First, we have polynomial functions. Those are functions that involve only constant multiples of positive integer powers of x. In the example here, the a's, a sub n minus 1, all the way down to a sub 0, those are constants. And then the powers on x would be 1, 2, 3, up to n. The degree of a polynomial is the highest power on x. So the way the polynomial is written on top here, the degree of p of x, we would say is equal to n. Some other quick examples. Polynomial x squared plus x plus 1 would have degree 2. The polynomial x to the 100 minus x to the 98 minus pi, that would have degree 100. Finally, we have a rational function, and that is a function that's the quotient of two polynomials. So we have a polynomial in the numerator and a polynomial in the denominator. So partial fractions is appropriate when we have a rational function to begin with. And in addition to that, we do need for the degree of the numerator to be less than the degree of the denominator. Now, of course, there are rational functions for which that's not the case. And in those cases, we can do some kind of algebra, perhaps long division of the two polynomials, to rewrite the rational function in the appropriate form. And finally, to see how to proceed when applying partial fractions, we need to have the denominator q to be completely factored into linear terms, repeated linear terms, and possibly some irreducible quadratic terms. All right, so we've set the stage for the types of functions partial fractions will help us integrate, and now we need to start taking a look at how we're actually going to go about it. Our first example will be an integral 4x plus 13 over x plus 2 times x plus 7. Now I want to point out that this is a rational function because we have a polynomial 4x plus 13 on top and a polynomial x plus 2 times x plus 7, which we could multiply out to give us a polynomial in the denominator. Furthermore, the degree of the numerator is 1, and the degree of the denominator would be 2, right? If I multiplied x plus 2 times x plus 7, the biggest power on x would be an x to the second, an x squared. So we want to see how we can split this rational function up into individual parts that'll be easier for us to integrate. And what we need to do is take a look at the denominator to figure out what the possible denominators for what we call the original fractions might be. Because the denominator here is already factored, it's not so hard to see that the two possible denominators are going to be x plus 2 and x plus 7. What we would like to do is take the original function and figure out how to rewrite it as some number a over x plus 2 plus some number b over x plus 7. If we can do that, then the integral will be much easier because we know how to integrate something like a over x plus 2. That would be the natural log of absolute value x plus 2. And same goes for b over x plus 7. We'll get some constant times the natural log of absolute value x plus 7. To find the a and the b, we have some algebra that we need to do, and we'll go through the steps required in the next example. Our task here is to find the a and the b that allow us to rewrite our rational function as the sum of two simpler functions. We begin, as we will all partial fractions decompositions, by clearing the denominators. And what that means is we're going to take the common denominator, x plus 2 times x plus 7, and multiply both sides of the equation by that common denominator. So that means we end up multiplying all of the terms by x plus 2 times x plus 7. And we do that because it allows us to cancel all of the denominators. On the left-hand side, notice that the entire denominator x plus 2 times x plus 7 would cancel, leaving us with only 4x plus 13. On the right-hand side, the x plus 2 would cancel with the x plus 2, but that would leave me with a times x plus 7. Similarly, for the second term on the right, the x plus 7s cancel, but that would leave me then with an x plus 2. So I get b times x plus 2. I'm going to distribute the a and the b on the right-hand side and collect my like terms. nothing happens on the left. But on the right, I get ax plus 7a plus bx plus 2b. Collecting like terms allows me to rewrite this as a plus b all times x plus the constant term 7a plus 2b. In other words, the term that doesn't have any x's in it. What I've done is collect the x terms together and also collect the non-x terms together. I haven't done anything on the left, so this is still all equal to 4x plus 13. Now, to make progress on solving for the a and the b, I have to recognize that in order for this equation to be true, the coefficients on x on the left and on the right have to be equal. In other words, the a plus b that's in front of the x on the right has to equal the 4 that's in front of the x on the left. So that gives me one of my needed equations. A plus b has to equal 4. The second equation comes from a similar observation that the constant or non-x term 7a plus 2b has to equal the constant or non-x term 13. So I have 7a plus 2b must be 13. That gives me two equations for my two unknowns, and that's enough to solve for the a and the b. There are a few different ways to go about solving for the a and the b. I'll start with the first equation, which allows me to rewrite, instead of a plus b equals 4, I'll do a is equal to 4 minus b. Then I can take 4 minus b and plug it in for a in the second equation. That's going to give me 7 times 4 minus b plus the 2b equals 13. Now I've got one equation and one unknown. That is something we know how to solve. I'll multiply through by 7. Collect my like terms together, so I have minus 5b is equal to negative 15. And that gives me b is equal to 3. Once I know b is equal to 3, I know a also, because a is equal to 4 minus b. So a is equal to 1. In conclusion, what we've done is we have shown that we could take a more difficult rational function, the original 4x plus 13 over x plus 2 times x plus 7, and we can rewrite that as the sum of two simpler functions. And this will be particularly handy when we go to integrate. It's useful at least once to check our work. So I'm going to do that here. And by check our work, I mean let's take the fractions 1 over x plus 2 3 over x plus 7, and add them together. And I'll get a common denominator. So I need 1 over x plus 2 times x plus 7 over x plus 7 plus 3 over x plus 7. Getting a common denominator here, I would multiply top and bottom by x plus 2. That gives me x plus 7 plus 3x plus 6 all over my common denominator of x plus 2 times x plus 7. And then in the numerator, x plus 3x gives me 4x. 7 plus 6 gives me the 13 I needed. And we see that we have done a good job by adding the individual fractions together. We came out with the original rational function. Once we have found the a and the b, as we did in the previous example, we use that to complete the evaluation of our integral. The original integral 4x plus 13 over x plus 2 times x plus 7, we have now seen we can rewrite as the integral of 1 over x plus 2 plus 3 over x plus 7. And now we have two integrals, each of which is much easier than the original rational function. As a final answer, we would have the natural log absolute x plus 2 plus 3 times the natural log absolute x plus 7 plus a constant. In the next couple of examples, we'll take a look at how to deal with simplifying inside the integral before applying partial fractions, and also what to do if we have a repeated linear factor in the denominator, like x plus 2 squared or x plus 2 cubed, and so on. In our next example, we have a rational function where the degree of the numerator is 2, the degree of the denominator is 3, so it is a suitable candidate for integration by partial fractions. The issue here, though, is that 1, the denominator is not completely factored. The x squared minus 1, we have to notice we can factor into x minus 1 x plus 1. And we can save ourselves some work if we notice that the numerator can also be factored. The form of the factors would have to be 2x plus or minus 1 and x plus or minus 1. So if we take x minus 1 times 2x plus 1, that would give us 2x squared. A negative 2x plus x would be minus x, and then 1 times negative 1 would be minus 1. So that's the correct factorization of the numerator. And that has the benefit of allowing us to cancel one of the terms in the denominator. So that's really going to simplify the problem, because instead of having 3 fractions to worry about, we'll be back to a familiar case where we only have 2. Our goal is, like it was before, we need to rewrite 2x plus 1 over x plus 1, x minus 2 as the sum of two simpler fractions, a over x plus 1 plus b over x minus 2. First step is to eliminate the denominators on both sides of the equal sign by multiplying through by the common denominator x plus 1 times x minus 2. On the left, the entire denominator cancels. On the right, the x plus 1 would cancel, but not the x minus 2 for the a term. And for b, the x minus 2 would cancel, but not the x plus 1. From here, I multiply through and collect like terms. So I'd have ax minus 2a plus bx plus b, and that has to equal 2x plus 1. Collecting like terms on the right, I have a plus b times x minus 2a plus b. And now I equate the coefficients. The a plus b is the coefficient on x on the right. That has to equal the coefficient of x on the left. So a plus b must equal 2. Similarly, the constant term on the right, minus 2a plus b, has to equal the constant term on the left, which is 1. So minus 2a plus b is equal to 1. I'll start with the first equation. If a plus b is equal to 2, then a is equal to 2 minus b. And if a is equal to 2 minus b, I can plug that into the second equation to get minus 2 times 2 minus b plus b is equal to 1, and that means minus 4 plus 3b is equal to 1. So b is going to be equal to 5/3. If b is 5/3 and a is 2 minus b, and a is 2 minus 5/3, or 6/3 minus 5/3, which is 1/3. So a is 1/3. Getting back to the original problem, my original integral is now equal to the integral of 1/3 over x plus 1 plus 5/3 over x minus 2 dx. And now each of those integrals, if I split it up into 2, those are both natural log integrals. I'll end up with 1/3 natural log absolute x plus 1 plus 5/3 natural log absolute x minus 2 plus a constant, and that should finish the example. Note that this function is appropriate for using integration by partial fractions. It's rational because we have a polynomial on top and a polynomial on the bottom. The degree of the numerator is 2 and the degree of the denominator is 4. So this is okay for integration by partial fractions. Now the presence of the repeated linear factor means that when we try to split the integrand into what we call the original fractions, we have to include a possible term for each of the powers of that repeated linear term. So not only might we have a fraction like a over x, but we might also have something like b over x squared or c over x cubed, and then the final one would be for the x plus 3 term. So our goal is to rewrite the integrand as the sum of these 4 fractions. Each of those would be a much easier integral than the original. We begin in the same way as for our other examples, where we write down the form we wish to get for the original function, and then we clear all of the denominators by multiplying left and right by the common denominator, which in this case is the x cubed times x plus 3. On the left-hand side, that denominator cancels. On the right-hand side, for my a term, I have an x in the denominator. That will cancel one of the x's in the x cubed, leaving me with a times x squared x plus 3. The b term has a denominator of x squared, so that would cancel with 2 of the x's in the x cubed. In other words, I'll just be left with x times x plus 3. My c term has a denominator of x cubed, which would cancel all of the x's, leaving me with c times x plus 3. And then finally d would have a denominator that cancels the x plus 3, but none of the x cubes. Now, on the right-hand side, I need to multiply everything out, collect my like terms, so I can then equate coefficients. If I distribute my ax squared, I get ax cubed plus 3a x squared. Then I would get a b x squared plus 3bx. I would get a cx plus 3c, and finally my dx cubed. All right, collecting like terms, I'll have a coefficient in front of the x cubed of a plus d. Right, I have 2 x cubed terms, ax cubed and dx cubed. As far as x squared terms, I have 3ax squared and a bx squared. That means I have 3a plus b times x squared. My x terms are 3bx and cx, so that's going to give me a 3b plus c times x, and then my only constant term is the 3c. All of that has to equal the x squared plus 2 on the left. Now we look at equating coefficients. I have a plus d times x cubed on the right, but I don't have an x cubed on the left. That means the coefficient for x cubed on the right has to be equal to 0, because there are no x cubes on that side of the equation. So I have a plus d must be 0. The coefficient on my x squared is 3a plus b, and that has to equal the understood 1, that's the coefficient of x squared on the left. So I have 3a plus b equals 1. And now, like the x cubed term, I have a 3b plus c on the right, but there is no x term on the left. That means the 3b plus c has to be 0. And then finally, my constant term 3c has to equal the constant term on the left, and that constant term on the left is just a 2. So I get 3c is equal to 2. That leaves me with 4 equations and 4 unknowns. The easiest one to start with will be the last. If 3c is equal to 2, then I know that c must be 2/3. If c is 2/3, I can use the third equation to figure out b. So I have 3b plus 2/3 is equal to 0. That's coming from this equation. If that's the case, then 3b is equal to minus 2/3, so that b is equal to minus 2/9. So I have 2 of my unknowns done. Now that I know b is equal to minus 2/9, I can use this second equation to figure out a. It tells me that 3a plus b is equal to 1. That makes 3a equal to 11/9. So a is 11/27. And now finally, if a is 11/27, then I can use the very first equation to figure out d. If a plus d is 0, that means 11/27 plus d is 0. So d is minus 11/27. Once we've found all of our unknowns, a, b, c, and d, it's a matter of just plugging those back in to our original decomposition and then doing the individual integrals. So our original integral would become, instead of a over x, it's 11/27 over x, and then minus 2/9 over x squared instead of b over x squared, plus 2/3 over x cubed, and minus 11/27 over x plus 3. Evaluating each of the pieces individually, I get 11/27 natural log of absolute x. And then using the power rule, the integral of 1 over x squared would be minus 1 over x. So I have negative 2/9 times minus 1 over x. Again, by the power rule, the integral of 1 over x cubed would be minus a half x squared. So I get 2/3 times minus 1 over 2x squared. And then the last integral is another natural log integral, minus 11/27 natural log of absolute x plus 3, plus our constant. With a bit of minor simplification, we end up with 11/27 natural log x, 2/9 times 1 over x, minus a third times 1 over x squared, and minus 11/27 natural log absolute x plus 3 plus a constant. And that finally finishes the example.